Hello everyone, welcome back to my channel. So today we'll be solving IBDP Chemistry HL Paper 2. This is of May 2022, time zone 1. So let's start with the first question. So when heated in air, magnesium ribbon reacts with oxygen to form magnesium oxide. So we have to write a balanced equation for the reaction that occurs, right? So basically what happens is our reactants are magnesium and oxygen. Magnesium is obviously solid, oxygen is a gas, and it will give magnesium oxide. Magnesium oxide, it's a solid. Now we just have to balance the reaction. In order to balance it, let's balance the oxygen first. Our oxygen is balanced. Now let's balance the magnesium. And that's it. That's the final answer to this question. Moving on to the next one. We have to identify a metal in the same period as that of magnesium that does not form a basic oxide. If we check in the period of magnesium, the only metal that doesn't form a basic oxide is aluminium, because aluminium, it forms an amphoteric oxide, which is both acidic and basic. So the answer will be aluminium. Moving on to the next one, we have a numerical problem here. So the reaction A was carried in a crucible with a lid, and the following data was recorded. We have the mass of crucible and lid. We have the mass crucible and the magnesium ribbon before heating, and we have the mass of the crucible, lid, and the product after heating. So we have to calculate the amount of magnesium that was used. So to find the mass of magnesium, we have to subtract this with this, right? Because we have to subtract the mass of crucible and lid from the mass of crucible, lid, and magnesium ribbon. That will directly give us the mass of magnesium, right? So that'll be 53.726 minus 47.372. If we do the calculations, we'll get 6.354 grams, right? Now that's the mass of magnesium that we have to find in moles. So moles of magnesium will be, we have to divide the mass with the molar mass, right? So 6.354 divided by 24.31. This will give me 0.2614. Sorry for that. Yeah, 0.2614 mole. And that will be the final answer to this part of this question. Now, in the next part, we have to determine the percentage uncertainty of mass of the product after heating, right? So, in order to find the mass of the product, we have to subtract the mass of crucible and lid from the last one, because that is the mass of crucible, lid, and the product. So, yeah, mass of product would be this minus this, so 56.941 minus 47.372. That will be 9.569 grams. Now, if we do the uncertainty analysis, what happens is when you subtract two quantities, the uncertainties get added up, right? So uncertainty will be it's a 0.001 for both of these cases. So 0.001 plus 0.001. This will be 0.002, right? Now, percentage uncertainty would be uncertainty divided by the mass of the product. I mean, the absolute mass of the product, which we got, that is 9.569. And we have to times it by 100 because it's a percentage. Upon solving, we will find it's 0.02%, which is the final answer to this part of this question. Moving on to the next part. We assume that the reaction E1 is only occurring and it goes to completion, but some product has been lost from the crucible. Just deduce the percentage yield of magnesium oxide from the magnesium oxide in the crucible, right? So we have to find the percentage analysis, right? So firstly, what we know is till now that the moles of magnesium which we used initially for this equation is 0.2614. So yeah, so moles of magnesium will be 0.2614, right? Now we have to find the moles of magnesium oxide. To do that, we have to write the stoichiometric ratio between Mg and MgO. So the stoichiometric ratio will be between moles of MgO by moles of Mg. This will be equal to, if we just go to the equation, it will be 2 by 2, right? So 2 by 2, that is basically 1. So I can just write moles of Mg. Oh, this will be equal to moles of Mg. That is equal to 0.2614. Now, this is the theoretical moles, right? I mean, theoretically, this much moles must be produced. I mean, this much moles of MgO must be produced. But yeah, obviously that wasn't produced. The product, like we have to find out the product moles later on. But yeah, let's find out the mass of MgO, which is the theoretical mass. That will be 0.2614 times the molar mass of MgO. The molar mass of Mg is 24.31. For oxygen, it's 16. So if we solve this, we'll get 10.54 grams. This was the theoretical mass of MgO. But actually, we got the mass. The mass that was obtained from the reaction is 9.569. So percentage yield will be the mass experimental mass by theoretical mass times 100 by mass theoretical and we have to times it by 100, obviously, because it's a percentage, right? So what's the experimental mass again? It's 9.569. So 9.569 divided by 10.54 times 100. So if I simplify this, you'll get 90.79%, which is the answer to this question. That is the percentage yield of magnesium oxide in this reaction, or in this experiment, I would say. Moving on to the next part. So when magnesium is burned in air, some of it reacts with nitrogen to form magnesium nitride. Obvious, and that's obvious because nitrogen is like a huge amount of our atmosphere is made up by nitrogen gas, right? So yeah, so there's the reaction. Obviously, the question is evaluate whether this rather than the loss of product to explain the yield found in part 3. So obviously, you see some of MgO wasn't formed, right? So what really happens is you have to do an yield analysis here. Now see, obviously, this is a reason why we got a less amount of products. Why is it so? Let's try to understand. Here we can see that 1 mole of Mg forms 1 by 3 moles of Mg3N2 from this reaction. And from the other reaction, we could say that obviously it was 1:1 ratio. So 1 mole of Mg would give me 1 mole of MgO, right? So 1 mole of Mg forms 1 mole of MgO. A molar mass of Mg3N2, if you calculate it out, it will be 100.95 gram per mole. Or I'll just use grams here, okay? Mass of Mg3N2 produced by the reaction of 1 mole Mg, that will be 1 by 3 of this mass, because 1 mole 1 by 3 moles is produced. So if you calculate the mass, that will be this, right? And if we simplify, we'll get it as 33.65 grams, right? So if 1 mole of Mg reacts with reacts with nitrogen to form Mg3N2, we'll see that 33.65 grams of Mg3N2 would be produced. But similarly, if I look for the mass of MgO produced by 1 mole Mg, this will be equal to like 1 mole Mg will produce 1 mole of MgO. So 1 times it will be the molar mass of MgO. Molar mass of MgO is 40.31, as we calculated it previously, so 40.31 grams. Now see, as lesser mass is produced when Mg reacts with N2, that's why this can be a possible explanation for the yield that is found in like the previous problem. So that's the answer. As lesser mass is obtained when Mg3N2 is produced or is formed. Hence, this could be a viable explanation of the yield found in the last part. That's it for this question. Now we can move on to the next one. So just an explanation other than product being lost from crucible or reacting with nitrogen that could explain the yield found in part B3. Yeah, there can be some easy explanation. For example, the reaction didn't reach completion, right? Like some amount of Mg remained unreacted inside the crucible. And another thing is the Mg which we used, it might contain some impurities. Now, obviously, the impurities didn't react, so it might also have impacted our yield, right? So there can be these two reasons, like the simple ones. The first one is the reaction didn't reach completion. So some amount of Mg remained unreacted. The second possible explanation is impurities might have been present in the reactant sample of magnesium. So these can be the two possible reasons. You can just write any one of them, and that will be enough. Moving on to the next question, we have to balance, presence of magnesium nitride can be demonstrated by adding water to the product. It is hydrolyzed to form magnesium hydroxide and ammonia. So firstly, we have to balance this chemical reaction. Yeah. In order to balance this, let's first balance magnesium and nitrogen. So magnesium, in order to balance magnesium, we have to put 3 here. In order to balance the nitrogen, we have to put a 2 here, right? Magnesium and nitrogen is balanced. We can put a 1 here. Now water, the number of oxygen atoms on the right hand side is 6, and the number of hydrogen atoms on the right hand side is 6 plus 6, that is 12. So oxygen is 6, hydrogen is 12. So if I put a 6 in front of H2O, that will technically balance the entire equation. Yeah. So I'll just cross check it again. Mg balance, hydrogen balance, oxygen balance. Yeah, that is perfectly fine. And that will be the final answer to this question. Moving on to the next part. Ammonia is added to water that contains a few drops of indicator. Identify an indicator that will change color, right? In order to do that, we have to find the pKa of ammonia. And that value of pKa is given in this in section 21 of the data booklet. So if I've just opened the data booklet here. So let's look for ammonia. Ammonia. Yeah. Ammonia has a pKb value of 4.75. I'll zoom in a bit. Yeah, zoomed in a bit, you can see the value is here, so it's 4.75. So pKb of ammonia is 4.75. Now, as the pKb of ammonia is 4.75, we have to find the pKa. How can we find the pKa? There is a classic formula that pKa plus pKb, this will sum up to 14 for any compound. So from here, pKa will be 14 minus 4.75. So our pKa will be 9.25. So we need to find an indicator from data booklet, section 22 of the data booklet, whose pH range contains the pKa value of 9.25. So if I head over to acid-base indicator, we see that 9.25, it will lie in this pH range, right? So we can use phenolphthalein as the indicator. So the answer to this question will be phenolphthalein. Phenolphthalein. Yeah, that's the answer to this part of this question. Now moving on to the next part, we have to find the oxidation state of nitrogen in Mg3N2 and NH3. Let's do for Mg3N2. We know that magnesium always has a +2 oxidation state. So 3 times +2. Let's assume that the oxidation state of nitrogen is X. Plus 2 times X, this will sum up to 0 because the net charge of this compound is 0. So 6 plus 2X equals 0. So 2X will be equal to -6. And for the simplifying, X will be equal to -3. So oxidation number of nitrogen in Mg3N2 is -3. Right? Or I would just write of nitrogen equals -3. Now if we do the same thing for NH3, let's assume that the oxidation number of nitrogen is X, and the oxidation number of hydrogen is always +1, like when it's bonded to a bonded to a nonmetal. This will be equal to 0. So X, if I simplify, X will be equal to -3. So also in NH3, oxidation number of nitrogen will be equal to -3. So that is the answer to part 3. In both the compounds, nitrogen will have oxidation state of -3. Moving on to the next part. We have to give reasons whether the reaction of magnesium nitride with water is an acid-base reaction or redox reaction, or both. I'll just write the reaction here: Mg3N2 plus 6H2O. This will give me 3MgOH whole twice plus twice NH3. Now let's analyze. Here we see that N3 minus ion, right? N3 minus ion in Mg3N2, this basically accepts H plus ions and forms NH3, right? We can say N3 minus ion. Sorry for that. Yeah. H plus ion to form NH3. So anyone who is accepting H plus, that is a base, right? So N3 minus will act as a base. This is acting as a base. Now H2O, we can see H2O is donating an H plus ion to form OH minus ion, right? So basically H2O loses H plus ion, so that is the property of an acid. So H2O works as an acid. Minus ion, this is the property of an acid. So yeah, obviously this is an acid-base reaction, so that's a yes. Now, is it a redox reaction? Now we have to check the oxidation states. Hydrogen everywhere has a +1 oxidation state. Oxygen, if you check in OH whole twice, it has -2. Oxygen and hydrogen didn't change their oxidation state. In the previous question, we checked that the nitrogen in both Mg3N2 and NH3 is -3, and also Mg has Mg2 plus +2 oxidation state in both sides. So we see that there is no change in oxidation state. No change in oxidation state for any element. Hence, I can say this is not a redox reaction. This is just an acid-base reaction. That's it for this part. Now let's move on to the next part. So most nitride ions are 14 N3 minus 8, the number of subatomic particles in this ion. So from the periodic table, we know that the atomic number of nitrogen is 7. So number of protons in nitrogen will be 7. How to find the number of neutrons? Number of neutrons is total mass number is 14 as given here, mass number minus the number of protons, that is 7. So number of neutrons will also be 7, and number of electrons will be number of protons plus the negative charge on the ion, so that is my minus 3. So we have 3 extra electrons as compared to that of the protons. That's why I'm adding 3 here. Number of electrons will be equal to 10. So 7 7 10, that is the answer to question E, part 1. Now moving to the next part, some nitride ions are 15N3 minus. State the term that describes the relationship between 14N3 minus and 15N3 minus. Now 14N3 minus and 15N3 minus, if we just check, they are the same element, right? But they have different number of neutrons or different atomic masses, right? So compounds with the same atomic number but different mass numbers is called isotopes. So yeah, same atomic number but different mass numbers. This is what we called isotopes. So that's it for this question. Yeah, now let's move on to the next one. Now nitride ion and magnesium ion are isoelectric. Determine giving a reason which has a greater ionic radius. Now the number of protons in nitride ions, that will be equal to 7, because the atomic number of nitrogen is 7, right? And for Mg2 plus, the atomic number will be I guess 12. So it will have 12 protons, right? So even if they are isoelectric, we see that there are more protons in Mg2 plus. As it has more protons, it has a greater nuclear charge, and we know in isoelectronic species, the species which have a greater nuclear charge, they will have a smaller radii, right? So Mg2 plus will have a smaller radii, and N3 minus will have a larger radii. So that's it here. So N3 minus will have a larger radii because so sorry for that. Yeah, it has a smaller nuclear charge as compared to Mg2 plus. Now that's it for this question. Moving on to the next one. Suggest giving a reason whether magnesium or nitrogen will have a greater 6th ionization energy. Let's write the electronic configuration of Mg. It is 1s2, 2s2, 2p6 and 3s2. And for nitrogen, the electronic configuration will be 1s2, 2s2, 2p3. Mg5 plus will have an electronic configuration of 1s2, 2s2, 2p3. Right? We are removing 5 electrons from Mg. Nitrogen 5 plus will have an electronic configuration of 1s2. So 6th ionization energy is basically removing an electron from the Mg5 plus ion or N5 plus ion, right? So if I remove from Mg5 plus ion, remove an electron from Mg5 plus ion, it will become Mg6 plus, and the electronic configuration will be 1s2, 2s2, 2p2. And from N5 plus, if we remove an electron, it will become N6 plus, and it will be 1s1. So here we see electron is lost from 2p subshell, while here electron is lost from 1s subshell. Now as 1s subshell is closer to the nucleus as compared to the 2p, so nucleus will be attracting the 1s electrons more strongly as compared to the 2p. So we would require a greater energy to remove an electron from the 1s as compared to 2s. Hence we can say that nitrogen will have a greater 6th ionization energy. Therefore, hence nitrogen will have a greater 6th ionization energy. Now we have to suggest 2 reasons why atoms are no longer regarded as indivisible units of matter. First reason is simple, that atoms can lose electrons to form ions, lose or gain electrons, right? So obviously, atom is losing something, so that is smaller than that of the atom. So yeah, that's one reason. Second is in nuclear fission, we see that atoms can split. A parent atom can split into two new atoms. So that's why atoms are no longer regarded as indivisible units. Now I'll just write out the answers here because form ions. Second is in nuclear fission, atoms can split to form new atoms. That's it for this question. If you just write these 2 points, you'll get a perfect 2 out of 2. In the next part, state the type of bonding in magnesium oxygen and magnesium oxide and how the valence electrons produce these type of bonding. So if we look at just the magnesium metal, the bonding type is a metallic bonding. How metallic bonding is formed, so it's just the basic definition, I mean the basic explanation. So Mg loses electrons to form cations. These electrons are spread throughout the lattice and attracts every Mg cation, hence holding the structure stable. The structure stable. That is it for this part. Now for oxygen. Now we know that oxygen gas exists as O2 O2 ion, that is O double bond O. That is oxygen. So we see that it's a double bond, so it's a covalent bond, right? And yeah, in covalent bond, what happens is if you have a double bond, so two electrons are shared by each oxygen atom, forming a double bond. So I can write like this: two electrons are shared by each oxygen atom, forming a double bond. Okay. Now magnesium oxide, MgO. There is an ionic bond between Mg2 plus and O2 minus ion. So the bond is ionic. How is this how is this ionic bond formed? So basically, two electrons are transferred from Mg to oxygen to form Mg2 plus and O2 minus ions. The electrostatic force of attraction between these two ions is basically the ionic bond. So that's it about question 1. Now moving on to the next question. They're saying here is magnesium is a reactive metal often found in alloys. So we have to suggest an experiment that shows magnesium is more reactive than zinc, giving the observation that would confirm this. It's very easy. So basically, we need to add Zn2 plus ion and Mg in a solution. So we can get Zn2 plus by adding ZnSO4, right? So if we make Zn2 plus and Mg in a solution, we will see that a black layer of zinc will be getting formed on the surface of magnesium, right? But if we do the other, the reaction in the opposite way, like if we make Mg2 plus and Zn in, in a solution, we won't see any reaction. So this proves that Mg is more reactive than Zn because it's displacing zinc from the solution, right? And zinc is not being able to do so. Hence, we can say Mg is more reactive. Yeah, I'll just type it out here. If we mix Zn2 plus, we can say like ZnSO4 with Mg in a solution, we will see a black layer of zinc getting formed on the surface of Mg, magnesium. But if we mix Mg2 plus and Zn, there will be no reaction. Hence, this proves Mg is more reactive than Zn. So that's all about 2A. Moving on to 2B. So magnesium is often used as a sacrificial node to protect steel from corrosion. So calculate the standard potential for a cell formed by magnesium and steel half cells. We can use the section 24 of the data booklet and assume steel has standard electrode potential of iron. So section 24. Here is section 24. We need magnesium and steel. Steel, they said to consider iron. So magnesium is this one, right? And for steel, iron, we can choose this one. So yeah, if I'll just write them here, Mg2 plus 2 electron gives us Mg. The E naught value will be minus 2.37. And Fe2 plus 2 electrons will give you Fe. The E naught value is minus 0.45 volts. Yeah. Now if I look at the net reaction, for the cell formed by magnesium and steel, will be Mg plus Fe2 plus. That will give you Fe plus Mg2 plus. The E naught value of this will be Mg to Mg2 plus. E naught Mg to Mg2 plus is just the reverse of this reaction, so no, the E naught value will be plus 2.37, and Fe to Fe, Fe2 plus to Fe is just this one, so minus 0.45. If we just add them together, we'll get 1.92 volts, and that is the answer to this question. Moving on to the next part, we have to find delta G of the reaction. Yeah, so delta G will be the formula of delta G that you can get from section 1. I mean, yeah, section 1 just contains the formula of delta G. And just verify it here. Yeah, this is section 1. So here you can see delta G. Just a second. Yeah, delta G is minus NF E naught. So that formula is from section 1. And from section 2, you can get the value of F. So the value of F here is this, which we can use in our question. Delta G is minus NF E naught cell. So N is the number of electrons that is transferred in this case, and in this case it will be 2, because it will be 2 electrons here. We are just adding, there is no multiplication. So yeah, 2 electrons getting transferred from Mg to Fe. N is 2. The value of F is, from here you can get it's 96500 coulomb, and E naught value from the previous question is 1.92 volts. So minus 2 times 96500 times 1.92. So if we just simplify, we'll get the value as minus 370.560 joules, and for the simplification it will give you minus 370.56 kilojoules. So we can obviously round it off to minus 371 kilojoule, and that will be the answer to this question. Yeah. Moving on to the next part, this cell causes electrolytic reduction of water on steel. State the half reaction of the half reaction of this reduction. Okay, so H2O plus electron, this will give us half H2 plus OH minus. This will be the half equation. Now if you want to make everything as an integer, so I mean every stoichiometric coefficient as an integer, so we can write it like this. That's it. And if you want to state the states, so hydrogen will be liquid, electron, H2 will be a gas, OH minus will be aqueous. So that's it for part 3. Let's move on to part 4. Now a graph of volume of gas produced by reacting magnesium with large excess of 1 mole per dm cube HCl is shown. Use the graph to reduce the dependence of reaction on the amount of Mg. So this graph basically gives us the gas volume with respect to time. So here we don't see anything regarding how the amount of Mg is changing, and yeah, with respect to the amount of products formed. So we can say that this reaction doesn't really depend on Mg, hence it's a zero order reaction. So it doesn't depend on Mg, so it's a zero order with respect to magnesium. Moving to the next part. This reaction is first order with respect to HCl. Calculate the time taken in second for half of Mg to dissolve when concentration of HCl is 0.5 mole dm cube, right? So basically, from the previous graph, we see that at around 400 seconds, okay, around 400 seconds, this reaction reaches equilibrium, right? Or we can say at around 400 seconds, like as Mg is our limiting reagent, at around 400 seconds, all of the Mg gets used up, right? So, yeah, this happens when we are using 1 mole per dm cube HCl. So what happens is, if we are using 0.5 mole per dm cube HCl, obviously it will take double the time because it's a first order reaction, right? So if we are using 0.5 mole per dm cube HCl, it will take around 800 seconds to reach equilibrium, or it will take 800 seconds for all of the Mg to get used up. So we need half of Mg to react. That means it will take half the time. So half of 800 will be 400. The answer should be 400. And yeah, I'm writing the explanation here. At 400 seconds, the reaction reaches equilibrium when 1 mole per dm cube HCl is used. When 0.5 mole per dm cube HCl will be used, it will take twice of 400, that is 800 seconds to reach equilibrium. And finally, so for half of Mg to react, it will take half the time half the time to reach equilibrium, right? 800 by 2, that is 400 seconds. So answer to this question is 400 seconds. Yeah. So carbonates also react with HCl, and the rate can be determined by graphing the mass lost. Suggest why this method is less suitable for the reaction of Mg with HCl. Now the main thing here is whenever gas is formed, what happens is the density of gas is very low. So the change in mass in the reaction mixture will be very low if gas is evolved, and hence it won't be a suitable method. So we can write it like this, as the density of gas will be low, hence change in mass of reaction mixture will be very low, and hence it won't be a suitable method. That is all about question 2. So let's slowly move on to question 3. In question 3, they are saying ammonia is produced by Haber-Bosch process, which involves the equilibrium N2 plus 3H2 gives you twice NH3. And yeah, there is a graph of percentage ammonia with pressure. So we have to reduce the expression for the equilibrium constant Kc for this reaction. It's pretty easy. Kc will be NH3 whole square divided by N2 times H2 whole cube. That will be the expression of Kc. In the next part, state how the use of a catalyst affects the position of equilibrium. Now, thing is, the catalyst doesn't affect the position of the equilibrium, it just speeds up the reaction. So, yeah, that's it. The catalyst doesn't affect the position of equilibrium. It just speeds up the reaction. Moving on to the next part, with reference to the reaction quotient Q, explain why percentage yield increases as the pressure is increased at constant temperature. Now, if the pressure is increased at a constant temperature, what happens is it will decrease the volume of the gas. You can get it from the ideal gas equation. If you increase pressure, the volume will decrease at a constant temperature. So yeah, what really happens is if the volume of the gas decreases, the concentration of all gases will increase. So if the concentration of all gases increase, we see that the denominator will increase more as compared to the numerator. As a result, what happens is the value of Q will be less than Kc. And hence the equilibrium will shift to the right and more products will be formed. And as a result, we will have like a greater yield or greater percentage yield. Just explaining it here. Increasing pressure decreases the volume of all the gases. Hence, the concentrations of all the gases will decrease. Okay, it will be increase, not decrease. Yeah. Now what happens is the denominator of the reaction quotient will increase more as compared to the numerator. Hence, Q will become less than Kc, and the equilibrium will shift to the right, forming more products. So that's literally all about this part. We can move to the next one. One factor affecting the position of equilibrium is the enthalpy change of the reaction. Determine enthalpy change of delta H of the Haber-Bosch process and use section 11 of the data booklet. Let's head on to section 11. Probably section 11. Yeah, that is section 11. It gives us the bond enthalpies, right? So for bond enthalpy analysis, we need to know which bonds are broken and which bonds are formed. So if we look at the reaction here, N triple bond, N bonds break, and N triple bond and HH bonds will break, and NH bond will be formed, right? So just make a list here. Bonds broken will be N triple bond N and H single bond H, and bonds formed will be NH. Now summation of bonds broken, this will be, so we see from the balanced chemical reaction, one N triple bond and one bond breaks and three HH bonds will break. So 1 times N triple bond N plus 3 times HH bond. The data booklet will get the values. So N triple bond N bond is 945 and HH is 436. So that will be 945 plus 3 times 436. It's 436, right? Yeah, 436, yeah. So if we simplify, we'll get that the summation of bond broken is 2253 kilojoules. In the next part, if we look at the summation of the bonds formed, we have to find the summation of the bonds formed, right? So that will be, so how many NH bonds is formed in one in the balance? So there is 3 NH bonds in one NH3, so there are 2, so rule of 6 NH3. I'll be 6 times NH, 6 times NH. NH will be which one? Nitrogen, and then hydrogen, that is 391. Yeah, or this one 391. So 6 times 391, that will be 2346 kilojoule, right? The enthalpy of this reaction will be summation of bonds broken minus summation of bonds formed. That is 2253 minus 2346. You just simplify, we'll get 9 minus 93 kilojoules. That will be the answer to this part of this question. Moving on to the next part. Outline the value obtained in B might differ from a value calculating using delta HF. So if we use delta HF, we are using the enthalpy of formation of the reactants and the products. But what happens is, if we use the bond enthalpies, then NH bond enthalpy is basically an average of all the NH bonds that are found in compounds, right? So it might not be precisely the NH bond enthalpy for NH3 molecule, and that's why these values might differ. Just write it here. NH bond enthalpy is an average of all NH bonds found in compounds. Hence, it might not be the precise value for NH bond in NH3, and that's the reason why you can have a difference. Now in this question, you have to demonstrate that your answer to part B1 is consistent with the effect of an increase in temperature on the percentage yield as shown in graph. We see that if temperature increases, we see that percentage, the percentage yield falls. Like for example, 350 at 400 atm, we had a 70% yield, and yeah, at 500 degrees, it's like somewhere a little bit above 20, so around 22 or 23. We had to explain why increasing in temperature decreases the yield. So basically what happens is, as the delta H is negative of this reaction from part B1, we can say that the reaction is endothermic. Now for any endothermic reaction, by La-Chatelet principle, an increase in temperature, the equilibrium will shift to the left and the yield of the products decreases. And also from the graph we can see that there is a decrease in yield as the temperature increases, and that's it. So we can just have an explanation here. For any exothermic reaction, increasing the temperature will shift the equilibrium to the left. And the yield will decrease, obviously, because less products will be formed. From the graph, we can clearly see a decrease in yield as the temperature increases. That's it for this part. Now let's move on to the next one. We have C1, the standard free energy change, delta G naught for Haber process Boss process is minus 33.0 kilojoules at 29 to 98 kelvins. Later isn't whether the reaction is spontaneous or not at 298 kelvins. Now clearly delta G is less than 0, and if delta G is less than 0, the reaction is spontaneous. So yeah, the reaction is spontaneous at 298 kelvins. Moving on to the next part. Calculate the value of equilibrium constant K at 298 kelvins. We can use the section 1 and 2 of the data booklet. So again, let's move on to section 1 of the data booklet. We can find the formula that relates the equilibrium constant to delta G. So yeah, we can use this equation. And on section 2, we can get the value of R. So let's start. We know that delta G equals minus RT ln K. Or simplifying, we'll get ln K as minus of delta G by RT. So that will be minus of minus 33,000. That is delta G in joules. Delta G was 33.0 kilojoules, right? So that is 33,000. R is 8.31 and T is 298 kelvins. If we simplify this, we'll get 13.326. That is ln K. Now K will be, if we have to just take an exponential, that is 13.326. Upon simplifying, we'll get 6.13 times 10 to the power 5, which is the answer to this part, of this question. Yeah. Moving to the next part. Here we have to calculate the entropy change for Haber process at 298 Kelvin. So entropy change, we have to use this equation. We have to find delta S. So delta G will be equal to delta H minus D delta S. So delta G is minus 33 times 10 cube joules. Delta H is minus 93 times 10 cube joules. T is 298 kelvins and delta S. Upon simplification, we'll directly get delta S as minus 201.34 joule mole inverse Kelvin inverse. This will be the answer. The next question here. Outline with reference to the reaction why the sign of entropy change is expected. So see, the entropy change here is negative. Negative means the randomness is decreasing. If we check the reaction here, we see that there is more gaseous moles on the reactant side as compared to that of the product side. So the number of gaseous moles is decreasing. As a result, the randomness is increasing, and hence delta S has a negative sign. So we can just write this is because the forward reaction involves decrease in the number of molecules of gas, which decreases the randomness of the system. Now coming to question 4, ammonia is soluble in water and forms an alkaline solution. So this is a given chemical reaction. So we have to state the relationship between NH4 plus and NH3 in terms of Bronsted-Lowry theory. So clearly we see that NH3 accepts an H plus to form NH4 plus. Anything that accepts an H plus is a base. So NH3 is a base. And NH4 plus we see is formed by NH3 accepting an H plus. And if we look at the other side of the reaction, or the backward reaction, NH4 plus donates an H plus to form NH3. So NH4 plus is the conjugate acid. So the relationship between NH4 plus and NH3 is conjugate acid base pair. That's it for part A. We can move on to part B. Determine the concentration of solution formed when 900 decimeter cube of NH3 at 300 Kelvin and 100 kilopascal dissolved in water to form 2 dm cube of solution. Okay, so firstly we have to find how many moles of ammonia is present in 900 dm cube of ammonia at 300 Kelvin and 100 kilopascals. We can use the ideal gas equation, that is PV equals nRT, to find the moles of moles of ammonia, sorry. So N will be PV by RT, right? P is 100 kilopascals, right? Volume is 900 dm cube, R is 8.31, and temperature is 300 Kelvin. If we simplify this, we'll get 36.1 mole. This is the moles of ammonia. Now we are dissolving this moles in 2 decimeter cube of solution. So concentration of solution will be the moles divided by volume, right? Volume is 2. The answer will be 18.05 mole per dm cube. And this will be the answer to part B. Moving to part C. You have to calculate the concentration of hydroxide ion in ammonia solution with pH equals 13, pH equals 9.3. So we know that pH plus P of OH, this will be equal to 14. So P of OH will be 14 minus 9.3. Simplifying, we'll get P of OH as 4.7. So OH minus concentration will be 10 to the power minus of 4.7. If we simplify this, we'll get 2 times 10 to the power minus 5 mole per dm cube, which will be the answer to this question. Yep. Moving on to part 2, calculate the concentration of ammonia molecules in the solution with pH 9.3, right? So yeah, let's try to solve this question. pH given is 9.3. So the reaction of ammonia, if you remember, it's like this. There's the this was the reaction given, right? The Kc equation will be, or the equilibrium constant will be, NH4 plus times OH minus divided by NH3 times H2O. If I multiply H2O on both sides, I'll get Kc times H2O. That will be NH4 plus OH times OH minus divided by NH3. Kc times H2O, this is called Kb, or the base constant, right? So this will be equal to Kb. Now, using the section 21 of data booklet, we can find the Kb value or pKb value of NH3. So 21, I guess, yep. So 21, yeah. Here we need to find the Kb value of ammonia. Ammonia Kb is 4.75. So 4.75. So Kb will be equal to 10 to the power minus 4.75. So we got the Kb value. Yeah. Now it's also given that pH is 9.3, right? So POH would be 14 minus 9.3. That will be 4.7 approximately. So OH minus concentration will be 10 to the power minus 4.7. And as OH minus is formed by the reaction of NH3 and H2, and OH minus and NH3 have the same stoichiometric coefficient, we can also say that the NH4 plus concentration will also be 10 to the power minus 4.7. Now plugging everything in the Kb equation, we will get 10 to the power minus 4.7 times 10 to the power minus 4.7 by NH3. This will be equal to the Kb. Kb, as we have found it as 10 to the power minus 4.75. But yeah, let's just keep it like this. Now if I simplify, we will get the value of NH3, or the concentration of NH3. Upon simplification, you'll find that the value of the concentration of NH3 is 2.24 times 10 to the power minus 5 mole decimeter cube. And this will be the answer to this question. Yeah. Moving to the next part, an aqueous solution containing high concentrations of both NH3 and NH4 plus acts as an acid-base buffer solution as a result of the equilibrium. Okay, referring to the equilibrium outline, why adding small volume of acid would leave pH of this buffer solution almost unchanged. So as a base, using the Henderson equation, we know that pH of a buffer solution will be pKb plus log NH4 plus by NH3, right? This will be the equation. Now, when a little amount of H plus is added, this equilibrium will shift to the right, and that will in turn decrease the H plus concentration. Now, as there is a large excess in the ratio of NH4 plus and NH4 plus divided by NH3, so this ratio will remain unchanged. Okay, so if I add a little bit of H plus, what happens is NH4 plus will increase a little, NH3 concentration will decrease a bit. So overall, what will happen is this ratio NH4 plus by NH3, this will more or less remain unchanged. As a result, the POH will remain unchanged. As a result, pH will also more or less remain unchanged. Yeah. So when a little amount of H plus is added, the equilibrium will shift to the right. Decreasing the H plus concentration. As is a large excess, the ratio NH4 plus by NH3 remains almost unchanged, and hence the pH remains more or less constant. that is all about part 3. Then we can move on to part D. Magnesium solves from slightly acidic solutions. Comment on role of Mg2 plus forming the MgOH plus ion in acid-base terms. Now we can see that Mg2 plus accepts a lone pair from OH minus ions, which makes it an electron acceptor. And we know that Lewis acids are electron acceptors. So hence Mg2 plus is a Lewis acid. That's overall it for this question. Moving on to part E. MgOH plus is a complex ion, but Mg is not regarded as a transition metal. Contrast Mg with manganese Mn in terms of one characteristic chemical property of transition metals other than complex ion formation. One property is that manganese can exhibit a number of oxidation states, while Mg only does exhibit a +2 oxidation state. So our property can be variable oxidation state, and the comparison is Mn being a transition element can exhibit a number of oxidation states, while magnesium has only +2 oxidation state in all its compounds. Now that's all for question 4. Now we can slowly move on to question 5. Question 5 is an organic chemistry question. So organomagnesium compounds can react with carbonyl compounds, and this is one equation. State the IUPAC name of compound B. So we have to write the IUPAC name. So first let's number the main chain. So there are three carbon atoms, and there are 2 substituents. One is the CH3, and there is one substituent CH3, and OH is our main functional group. So this will be from the main chain, it will be propan 2-ol, and at the 2 position there is a methyl, so the name will be 2-methyl propan 2-ol. Now moving on to the second part. Compound A and B are both liquids at room temperature and pressure. Identify the strongest intermolecular force between molecules of compound A. Now looking at compound A, obviously this compound is a polar compound because oxygen is more electronegative than carbon. So as compound A is a polar compound, the strongest intermolecular force between it will obviously be the dipole-dipole interaction. So yeah, as compound A is a polar compound, the strongest intermolecular force between 2 polar compounds is dipole-dipole interaction. Moving to the next part, we have to find the number of sigma and pi bonds in compound A. So just remember, one single bond contains 1 sigma bond, double bond contains 1 sigma and 1 pi bond, while triple bond contains 1 sigma and 2 pi bonds, right? So here we have to count the number of single and double bonds. In compound A, we see that there is only 1 double bond, so number of pi bonds is 1. Now we have to count the number of sigma bonds. So there are three carbon hydrogen bonds, so that's 6. This one is 7, this one is 8, and 1 sigma bond here, 9. So there are a total of 9 sigma bonds in compound A. The next one, you have to deduce the hybridization of central atom in compound A. How to find the hybridization? So we have to first count the number of sigma bonds around A, and that will judge the hybridization. So around the central atom, so this carbon is the central atom. The number of sigma bonds around this carbon atom is 1, 2, 3. So there are 3 sigma bonds around this carbon atom. 3 sigma bonds around the central atom. As there are 3 sigma bonds, the hybridization will be sp2. That's it here. Next part. Identify isomer of compound B that exists as optical isomer or enantiomers. So compound B is this. So yeah, that's pretty much simple. So this compound will be the optically active isomer of B. Yep. Moving to the next part. Why will it be optically isomer? Why will it be optically active? Because around this carbon, we see that all the 4 groups are different. Hence, this is a chiral carbon, and This will show optical isomers. The compound B can also be prepared by reacting an alkene with water. The formula of the alkenes is again pretty much simple. So water molecule is at the center, so you can place the double bond anywhere in the compound and you will get the correct answer. All right, next one. Explain why the reaction produces more more of this compound rather than this one. Now we have to look at the Markovnikov's rule. What happens is, if we look at the mechanism of this reaction after step 1, what happens, 2 carbocations will be formed, right? So step 1 will be CH3. So yeah, step 1 will be an H plus will be added, right? So there can be two carbocations which could be formed. So either this carbocation will be formed or this carbocation will be formed. Now we see that due to greater inductive effect, let's say this is carbocation A, this is carbocation B. Carbocation A is more stable as compared to carbocation B. Hence, in step 2, more of carbocation A is converted to products. You can also write the step 2 here. That's all about this question. Now moving to the next part. Due to the structural formula of repeating unit of polymer from this alkene. That is simple. So basically we have to open this double bond, and yeah, will definitely look like this. So this is our compound, right? So the repeating unit of this polymer is we have to open this bond. So yeah, it should look like this. This will be your answer. Deduce what will be observed when compound B is formed with aqueous potassium dichromate 5. Now potassium dichromate 5 is a strong oxidizing agent, right? In compound B, you see, yeah, this is compound B, right? In compound B, you have a tertiary, this OH is attached to a tertiary carbon atom. So we cannot further oxidize it to any ketone or any carboxylic acid. So hence there will be no reaction. So potassium dichromate 6 is a strong oxidizing agent. But as the OH is attached to a tertiary carbon, there is no room for the production of aldehyde or ketone or carboxylic acid. Hence, there will be no reaction. That is part C. Now moving on to part D. Iodomethane is used to prepare CH3IMG, which can also be converted into methanol. Right? Identify this type of reaction. So obviously we see that I is getting substituted by OH minus, so that's a substitution reaction. And as CH3I is attached to a primary carbon, this will be a SN2 reaction, right? So we can say it's a SN2 reaction. Outline the requirements for a collision between reactants to yield products. So there are basically two requirements. First requirement is energy of reacting molecules. This should be greater than the activation energy of the reaction. Reaction, this is the first condition. Second is, while collisions, these reactant molecules should be at a correct orientation. During collision, should have a correct orientation. That's also all about this part. Move on to the next part. Explain the mechanism of the reaction to represent the movement of electron pairs. So this is the wedge and dash structure of CH3I, right? Now I is more electronegative than carbon, so I will have a slight negative charge on it, while carbon will have a slight positive charge on it. When OH minus comes in the vicinity, this OH minus will be attracted by this carbon atom because it's a positive charge, it's a negative charge. So OH minus will first attack this carbon, and this carbon will start breaking the bond with this iodine. As a result, firstly this intermediate will be formed, where you see a bond with carbon and OH is getting formed, while a bond with carbon and iodine is getting broken, and there will be a net negative charge on this compound. And finally what happens is this iodine will leave, okay, as the bond will break, and we will have a final structure like this one. So this is the entire mechanism. The polarity of carbon halogen bond facilitates attack by OH minus, and outline given is how polarity changes going down the group. Now what happens is while we go down the group, the electronegativity decreases. So hence as the electronegativity decreases, the difference in electronegativity decreases, and hence the bond polarity also decreases. So yeah, going down group 17, electronegativity decreases. As a result, the difference in electronegativity between carbon and the halogen atom decreases, and hence the bond polarity decreases. Right. Now moving to the last question. Nitric acid is produced by oxidation of ammonia. First we have to draw arrows and boxes to represent the electronic configuration of nitrogen atom. Nitrogen has a total of 7 electrons in neutral nitrogen atom. So 2 electrons will get filled in 1s, 2 in 2s, and 1, 2, 3 electrons will get in 2p. So that's the electronic configuration of nitrogen atom. Next part, deduce the Lewis structure of nitric acid molecule that obeys octet rule, showing in any non-zero formal charges on the atom. So the Lewis structure of HNO3 is pretty much common. It looks like this. We also have to show the electrons, right? I mean lone pair electrons. This will be one, and then this will be the other one. Now this is the possible Lewis structure or electron dot structure of HNO3. Explain relative lengths of 3 bonds between N and O in nitric acid. Now firstly we see that N and OH bond is a single bond, right? So single bonds will have the highest length. So first part is NOH bond length will be longer than NO bonds. This is the first part. Now what happens is, due to resonance, because of possible resonating structures, we'll see that the NO bond lengths are basically equal. So second is NO bond lengths are equal. So that's all about the relative lengths, right? State a technique that is used to determine the length of bonds between N and O in solid HNO3. Firstly, we can use X-ray crystallography. That's the method to basically determine covalent bond lengths. So yeah, then the next part. A mixture of nitric acid and sulfuric acid can be used to convert benzene to nitrobenzene. Write an equation for reaction between these two acids to produce the electrophile NO2+. So basically HNO3 plus H2SO4. When they react, NO2+ is produced, H2O is produced, and HSO4- minus is produced. So there is a complete balanced equation. Draw the structural formula of carbocation intermediate produced when this electrophile attacks benzene. So yeah. So if this is benzene molecule, so this double bond will attack the NO2+, and we will have this type of compound, right? Now we will see a few resonating structures, like yeah, this one here, Okay, this will be an equivalent sign here. There's also a hydrogen attached. So yeah, the carbocation intermediate will look like this. So we see that the positive charge travels from this point and ends at this point. So this is the path of the positive charge. So positive charge, and here you have NO2 and here you have hydrogen. So this is the structural formula of the carbocation intermediate that will be formed. And the last question, reduce the number of signals that you would expect in 1H NMR spectrum of nitrobenzene and relative areas of these. Now, if I look at nitrobenzene, we have to find the number of different hydrogen in the benzene molecule, right? So if this is our reference point, we say that these two hydrogens are equivalent. Equivalent, they will produce one signal. Again, these two are equivalent, right? So they will also produce one signal, and this one will also produce one signal. Total 3 signals will be produced. Now the relative areas. Now see these two signals, as they have, there are 2 hydrogens each, and there is 1 hydrogen here. So this will be 2:2:1, right? So yeah, the relative areas will be 2:2:1. And that's the last question. Thank you so much for watching the video. I'll soon be posting the solution for time zone 2, paper 2, and also the paper 1 of chemistry. Thank you so much again.